All right, the last part of this is going to be the Daylight Hours Explorer. And we're going to take a look at a graphic that shows us the number of daylight hours over the course of the year for different latitudes. We'll start with 0, and then we'll do some other latitudes as well. We will record the number of daylight hours. Remember, our day is always 24 hours, but how many of those hours are daylight hours is going to vary. Then you will calculate the range, which is just your biggest number minus your smallest number. And the range is going to tell you how much the number of daylight hours is varying over the course of the year. Okay, so you're going to not see me write these down, so you're just going to have to pay attention and follow along. Hit pause when you need to, that kind of thing. All right, so we're going to move over to the Daylight Hours Explorer. And on the y-axis, we have the number of daylight hours, and then it's highlighted for whichever date you've picked. And then along the x-axis, we have the day of the year. Over here, we have the latitude, and here we just have a globe depicting where our latitude is that we're dealing with. Okay, the gray area is the portion of your 24 hours that's nighttime. The kind of pale yellow area is the portion of your 24 hours that's daytime. All right, we're going to start at 0 degrees, so living at the equator, and we're going to start at March 21st. All right, at March 21st, remember, is an equinox, so everybody's pretty much going to have 12-hour days. 12 hours of daylight, 12 hours of darkness, so make sure you record that. And you notice that this line here stays perfectly straight. And that should tell you that even when we move dates, our number of daylight hours is staying the same. So we come over here, this is the June solstice. For us in the northern hemisphere, that would be the summer solstice. But still, we only have 12 hours of daylight, and then we'll have 12 hours of darkness. And again, it's not going to vary when you're living at the equator, which is where we are right now. September 22nd, this would be the northern hemisphere's fall equinox. If I can get it on the 22nd. Nope, it's not going to let me. But it's still 12 hours. And then come all the way over here to December 22nd. That's the northern hemisphere's first day of winter. But again, we're at the equator right now, so still 12 hours of daylight. Okay, to calculate the range, well, the biggest number that you just recorded for 0 degrees was 12 hours. And the smallest number that you just recorded was 12 hours. And 12 minus 12 is 0. So your range at 0 degrees is 0. And that just says that, your number of daylight hours does not vary, does not change over the course of the year if you're living at the equator. But now we're going to go to 30 degrees north. And let's see, March 21st. So we live at 30 degrees north, and now we have a little bit of a wave to our graph. March 21st, again, it's an equinox, so it's going to be 12 hours of daylight. For us in the northern hemisphere, June 22nd is our summer solstice, and it's also our longest day of the year. If you're at 30 degrees north, your longest day of the year is about 13.9 hours, so just under 14 hours of daylight. Okay? And then the September equinox is going to mark our first day of fall. And again, it's an equinox. 12 hours of daylight, 12 hours of darkness for pretty much everybody throughout the world on that particular day. Then we're going to go to the December solstice, which is our first day of winter. And since it's our first day of winter, it's also our shortest day of the year. We only have 10.1 hours of daylight on that day. Okay. Once again, for 30 degrees north, you've written in the daylight hours, take the largest number, subtract the smallest number, and record the range. And that's going to tell you how many hours. It varies from your longest day of the year to your shortest day of the year. All right, then we're going to switch to 30 degrees south. On this simulation, 30 degrees south is just represented by a negative. And watch what it does to the graph. It just simply flips it. All right, so for 30 degrees south, December 22nd is actually the longest day of the year, okay, because that's their first day of summer. So make sure you put that where it says December 22nd, and we'll kind of work our way backwards. September 22nd will be the equinox. For folks in the southern hemisphere, that's going to be the spring equinox. For us here in the northern hemisphere, it's our fall equinox. But everybody's pretty much having 12 hours of daylight and 12 hours of darkness. Then we go to the June solstice. And for folks in the southern hemisphere, that's going to be their shortest day of the year. That's their first day of winter. And they only have 10.1 hours of daylight that day. And then back up to March 21st. And again, March 21st is an equinox, so everybody, no matter where you are, is pretty much having 12 hours of daytime, 12 hours of nighttime. Notice the information that you recorded for 30 degrees north versus 30 degrees south, and you should notice that pretty much your data is switched. It's flipped. Okay? All right, the next latitude that we're going to look at is 60 degrees north and 60 degrees south. All right, 60 degrees north. March 21st, we're going to have 12.1 hours. So basically, we're still at 12 hours because it's an equinox. But notice that the graph is even curvier than it used to be. By the time we reach the June solstice, the summer solstice for us here in the United States and the Northern Hemisphere, come on, we're having long days, 18.5-hour days, okay? And then the days get shorter until we get to the September 22nd equinox. For us in the Northern Hemisphere, that's our fall equinox. Again, about 12 hours of daylight. And then, by the time we get to the December solstice, folks that are living way up here in northern Canada, on the December solstice, the shortest day of the year, they're only going to have about 5.5 hours of daylight, and the rest of it's darkness. Okay? So hopefully you can predict what the opposite, the southern hemisphere, is going to look like. Let's flip it to the southern hemisphere. Okay, and you basically get the opposite. March 21st, you have 11.9 hours, so that's basically 12. And then the June solstice for the southern hemisphere is actually their shortest day of the year, only 5.5 hours of daylight. The September equinox, about 11.9 hours of daylight. That's basically 12. The December solstice, this is going to be their longest day of the year. Okay, 18.5 hours of daylight. And if you notice the 60 degrees north versus 60 degrees south, you'll notice that your data is basically flip-flopped. Do not forget to calculate the range and record it. Now, I'm not going to do 90 degrees north and 90 degrees south, but I do want to show you what's going to happen to these curves as I make my way further and further towards the poles. So here's 60 degrees north, and we're only having a 5.5 hour day for our shortest day of the year. If I go to 62, just 62 degrees north, I'm already down to just 4.7 hours of daylight on my shortest day of the year. If I go to 64 degrees north, I'm down to only 3.6 hours of daylight on my shortest day of the year. If I go to 66 degrees north, I'm down to less than 2 hours of daylight on my shortest day of the year. And watch what happens if I get to 67 degrees north. I have a time in the year close to the winter solstice when the sun does not come up above the horizon. So I have basically a time period where I'm going to have 24 hours of nighttime, okay, for a small portion of the year. I also have another portion of the year around the summer solstice where I have 24 hours of daylight, okay? And that's just simply because I'm so close to the poles, okay? If I go to 70 degrees north, the amount of time that I'm having 24 hours of daytime or 24 hours of nighttime gets even bigger. Okay? The last question of the page is actually number 1 under this chart. What is the relationship between the distance from the equator, meaning latitude, and the amount of variation over the course of the year? So if you go back to this table, as your distance from the equator increases, like as it goes from 0 to 30 to 60 to beyond, the amount of variation, what does it do? Does it go up? Does it go down? What does it do? So please write a complete sentence stating the relationship between latitude and the amount of daylight variation. You might want to start your sentence with something like, as latitude increases, the amount of daylight variation, and then you tell me what it does. Okay? And that should wrap it up